We present perception-informed autonomous environment augmentation with modular robots. This video showcases hardware experiments from our paper. In each experiment, the robot acts autonomously using only onboard sensing. Each video was shot in one take. In experiment 1, the robot begins in an office with a desk and set of drawers. The robot is searching for some missing objects, which might be inside the drawers. Its high-level task is to open the first drawer and, if possible, climb on top of the first drawer, open the second drawer, and take a picture of what's inside. The robot quickly locates the pink label that identifies the set of drawers. It moves into place, latches to the bottom drawer with its magnets, and pulls it open. To determine whether it can climb into the bottom drawer, the robot moves to an appropriate vantage point to inspect the drawer with its RGBD camera. Once it gets a good look, the robot can see that the drawer is full of books. As a result, the environment characterization tools identify the open drawer as a ledge-type environment with a height of 16 centimeters. Based on environment characterization, the high-level planner recognizes that this ledge is too high for any configuration in its design library to climb. However, it also identifies a pre-built ramp structure near the drawer. Recognizing that the ramp structure can be used to overcome the ledge obstacle, the high-level planner commands the robot to retrieve the ramp. It backs up to take another look at the ledge, confirming an appropriate placement location for the ramp. It then places the ramp next to the drawer, augmenting this previously problematic environment to make it possible to complete its task. The front three modules break off and climb onto the books. Once on top, localization is provided by the downward-facing RGB camera on the sensor module. The modules orient themselves to face the second drawer, latch to it using their electropermanent magnets, and pull it open, allowing the sensor module to take a picture of the missing objects. In a second version of the experiment, the bottom drawer is empty. When the robot observes the drawer, it no longer classifies it as a ledge that can be climbed. This makes it impossible for the robot to complete its mission, whether or not a ramp is available. To indicate that its mission is impossible, the robot disassembles itself. In experiment 2, the robot begins on the left table and is simply tasked with moving to the pink goal marker on the right table. The robot immediately recognizes that the goal marker is isolated from its own location by a 16 centimeter gap between the two tables. Recognizing that it would be unable to cross this gap on its own, the robot searches for materials to augment its environment. It identifies 3 available augmentation modules nearby and assembles them into a bridge. Once the bridge is assembled, the robot maneuvers to one of the bridge placement candidate points identified by its environment characterization algorithm. Before placing the bridge, it runs environment characterization again to ensure precise positioning. It places the bridge across the gap, then reconfigures, and crosses the bridge, completing its mission. Thank you for watching.